Thank you, guys. All right, the next aspect of our game involved animation, which we used the University's motion capture lab to do the majority of those, if not all of them, I'm pretty sure. And Michael and Eric were the ones heading that up, and I'd like for them to come describe their experience and tell you all about it.
I'm Michael Ardoin.
And I'm Eric Killen. As I said before, we're the two that handle the animation portion of this video game project. We did most of the work in the motion capture laboratory using the Vicom Blade software. As you can see, there's an example image of it. It's a system that allows you to record animations from characters that are wearing a capture suit. As for an example, let's click forward. This is our primary model actor Paul in the motion capture suit. You can see these cameras on the side here. These are infrared cameras that will basically all these little points on here, these white spheres, they reflect the light off it, and the same infrared cameras capture that reflection and plot them as points. And using these points, we'll have it basically the information will initially look like this. As just a engram of dots and stuff. There's not much you can make out of it. But once it's keyed to Paul's body, this we run it through a labeling tape, which will take every point and try to determine whether it belongs to this part of the body or that part of the body, and thus try to reconstruct a model and a skeleton from that. So this middle image is Vicom's attempt to create a skeleton on its own, and it usually doesn't do a stellar job of this. So the two of us had to go through each animation and clean it up frame by frame until it completed. And this is a example of the completed model once it's fully done in Vicom Blade. And for the next panel. And it's another example of a completed skeleton map.
Alright, after we complete the models in Vicom Blade, we import the models, the skeleton in the Motion Builder. And Motion Builder is a 3D animation software that lets us create and edit videos and video game animations. And what we do with the skeletons, we grab them, we plot them onto the actual models that we'll be using. That way the skeleton and the model move as one, and we can actually move show the animations on an actual character instead of just the skeleton that we plotted it onto. And through Motion Builder, you can fine tweak the movements of the model. So if in Vicom Blade you have jitters or the leg will move slightly, you can edit those motions in Motion Builder to fine tune it and get the motions exactly how you want them to be. And after we cleaned up and graphed everything to the models on Motion Builders, we moved it from Motion Builder to Maya. And through Maya, we put the actual textures and the skeleton together, and it'll make the character that we use in-game. So through this process, we'll have a complete skeleton that'll do all the actions that we need it to do. And let's see, through a combination of Vicom Blade, Motion Builder, and Maya, we have all the animations that our characters do for abilities and movement, running, jumping, all the things that are necessary to make a game actually function the way it should function.
Thank you, guys. All right, and our next aspect of our game is going to be our particle generating software. It's called Particle Universe. It allows us to create particle systems, which we use in-game that control how things are visually drawn to the user. Particle Universe has a lot of fine-grained controls that allow you to manipulate these systems. And I'd like for Mike and Paul to come up and describe their experience using Particle Universe since they headed up that project.
All right, with Particle Universe, it's a software that allows you to manipulate materials and textures and colors in certain particles and make a system of them. So the way it works is you have a particle system and you use renderers, effectors, emitters, and observers and handlers to actually emit particles in a certain way using mathematical formulas like radius, and you'll tell it what's the velocity you want it to have, what kind of gravity effect, what effects gravity will have on it, and what colors it'll take on, what textures it'll have during the process of actually making the system. So by changing certain variables in the system itself, it'll actually make different particles that emit different ways and make different colors.
Here you can see 3 different particle systems that we made. The first one is a particle system for when a user is about to cast a technology spell. We have an indicator to show which spells you're about to use, and the one in the middle is a particle system for an enemy that we were going to use in the game. And the third one is our vortex particle system. And here's our video about making particles systems. Here's our revive particle system. And here you can see the different techniques. The techniques are, you set up which materials you're going to use, how big the particles are going to be, how much you want the technique to emit. Here you can see I use swirl, that different dimensions of the particles. Here is the renderer. It tells the particle system how the particle is going to be shown to the user, which dimensions are up, which dimensions down. This is the emitter. This tells you how fast the particles are emitted in the particle system, how many particles are emitted at once, how fast they're going, the color, how long they're alive for. That's about it.
Thank you, guys. The next aspect of our game is sound. You can't have, just about any game, you can have sound involved with it. So we had Kevin and Paul working on that.
Hi everyone, I'm Kevin Swear.
Paul. We didn't have a musician in this 427 class. They usually do. So we went online and found royalty-free websites that have different sound effects and background music that we could use in the game. And we also have the repository from former 427 classes, which we could use for the sound effects in the game.
So since we had to get our sound from multiple sources, there was a lot of inconsistency between them. So we used Adobe Audition in order to clean up a lot of the sound, whether it was making some of them louder or lower in volume. We also used it to make a few composite sounds. An example you can see on the screen right now, what I'm doing is I'm working with 2 sounds to develop audio for, it was an electrical storm combat effect. So we had kind of an electrical static, and we combined thunder with that. So once we got all the sounds the way we wanted to, we had to bring them into the game. And to do that, we used Ogre's Sound Manager. And we found a plugin called Fmod. And we were able to combine those to make it incredibly simple to put sound in the game.
Thank you, guys. Okay. The next aspect of our system is going to be our shading that we're going to be applying to our different models in game. And Steven's the one that headed that up, and I'd like for him to come and kind of describe what he did.
I'm Stephen Killingsworth. I worked on the shaders for our game. Most of our shaders, or all our shaders, are written in either DirectX or OpenGL. Some of them overlap so that they're written in both DirectX and OpenGL. Ogre makes it really easy where you can switch between the 2 rendering contexts. So if you wanted to port it over to another system, OpenGL is more of a cross-platform thing, whereas DirectX more aimed at Windows, but Ogre lets you flip between the two. Ogre makes it really easy to write your shaders between DirectX and OpenGL because it sort of insulates your shaders away from the setting up of the rendering context, whether that be DirectX or OpenGL or even CG. So all you have to focus on is the direct coding of the shader strings. Some of the shaders that we implemented in our game are the toon shading, which is sort of a way to sort of work with the chibi style of our character. Since the chibi is more of a hand-drawn, style, we wanted to make it look like a cartoon. So the toon shading sets a gradient on the colors that you see on the model. And I thought it looked it worked pretty well with it. And another shader that it was a sort of a post-processing filter that we had working in OpenGL but couldn't quite port over to DirectX is an edge appenssion shader, where it sort of outlines the model itself to distinguish it from the world. And it gives it it sort of emphasizes that hand-drawn feeling. Another one of the shaders that we implemented are the procedural noise shaders. I figured that with the abilities that we had, noise shaders that you'd apply directly to the body of the mesh would be a good way of giving the player feedback that, hey, you're under a certain status effect. So the examples that you see on screen are, the green one is the poison status effect. So if the player comes under, he gets poisoned, he'll have this green glowing thing on him. Or if he gets stunned, he'll have the yellow glowing thing. And I made sure to make it where it was easy to make more of these noise shaders and just slap them on right after you made them because they're rendered in multiple passes. So you render out the model just with the toon shading and the texturing, and then you go back in and you write over, or you rewrite the noise shader, and it just doesn't write upon the pixel that it didn't generate a noise shader or a noise pixel for. And you can also you can add two noise shaders together. You can add as many as you want together. Actually, like in the bottom right example, you see the poison shader and the other one's sort of a burn shader, and they're working together, and you don't really experience too much of a slowdown or having to re-render the whole model again and again. Here's a quick video of some of the noise shaders just being applied and animated. And also this shows off some of the other textures that our artists worked on to be applied to the model. One of the other shader types that we used were normal mapping shaders. Normal mapping is a technique that's used to create it creates really detailed models without having to worry about an increase in poly count. So even though you have a model that looks like it's made up of a lot of very detailed things, sort of with this stone map, it looks like all these stones are individual polygons, but what's actually happening is the whole cube is just a flat cube. And then you go back and you normal map things, and it tells, whenever you calculate the lighting on the object, it sort of tricks the eye and makes it look more detailed than it actually is. You can kind of tell, like on the edge of this vase, that's just a flat line, whereas in the middle of the vase, it looks bumpy. The tool that I used to sort of speed up writing these shaders is a tool called RenderMonkey. It's developed by AMD. It's sort of like Ogre in that it sort of separates out the rendering context, so you don't have to worry about setting up DirectX or OpenGL, which is kind of a hassle, especially if you want to be able to work between the two. So RenderMonkey just lets you write whatever shaders you want. You still have to write GLSL and HLSL separate code, but you can switch between the two shaders. It even makes passing in uniforms or specific variables that you need in your shader script very easy, and it even has automatic uniforms where if you have a shader that's dependent on time, you don't have to worry about updating your time every frame or so. It just works. It automatically does it for you. And the tool that I use to generate normal maps for the bump maps is Crazy Bump. It's a tool called Crazy Bump. And it's really special in that you just give it a flat color map, sort of like this brick texture right here. That's just a photo that I had. And you feed it into Crazy Bump, and Crazy Bump will give you, it'll just spit out the normal map for you, and even give you an example of what it looks like if it was plastered onto a sphere, or whatever else you'd want to give it. And it also is able to generate displacement maps, normal maps, and occlusion maps, or any other sort of maps that you might need. And it also gives you a bunch of properties that you can adjust to fine-tune your normal map. And those were some of the shaders that I wrote for this. Yeah, that's it.
Thank you, Steve.